Okay, I've not been recording maybe. So given this equation here that y is equal to s sine omega 2 pi into t out of 0.1 minus x out of 2.0, determine the velocity. Determine the velocity. So our general equation that we've just discussed was saying that y, the equation is given by y is equal to a sine omega t minus the phi. Remember this? I'm just reminding you. So in terms of the pi, we shall simply have our y being equal to a sine 2 pi out of the capital T times the t, then minus 2 pi out of the wavelength times the distance x. And this will give us y is equal to a sine 2 pi into brackets t out of the capital T minus x out of the lambda. So when we try to look at this equation here and relate it with this one here, you can find the velocity. So how do you find the velocity? What is the equation for the velocity? What do you remember? In short, the wave equation. How did we state the wave equation sometime back? It was given as the lambda times the frequency.
Yeah.
The wave equation. We've seen something like that before.
Yeah.
Yes.
Just
Okay.
picking up by trying to understand this other thing.
By our equations here. So we've gone back to the basics. That the wave equation V is always given as lambda times the F. So when you compare these two equations here, this one and this one, what is our wavelength?
2.0.
2.0, correct, in meters. And then what is our frequency? How do we get the frequency? What is the equation for the frequency?
1 over t.
1 out of the capital T. That is 1 over the periodic time. And the periodic time, when you compare, the same as 1 out of 0.1. It will give us 10 Hz. Okay?
Yeah.
Therefore, our velocity therefore equal to lambda is 2 times 10, and this will give us 20 meters per second.
Oh,
so
easy.
Okay. Okay. It's easy. What was making it be hard?
Like honestly, like this equation,
Put everything together.
This side completely me lost. I thought we are going to like cross do some simultaneous equation or something.
So in other words, we just use this general equation here to compare and get out what we need from the given equation. Maybe the periodic time, maybe the wavelength, maybe the amplitude. Like that, just simply compare and get the equations that we need, the quantities that we need from the. Okay, so that is part A. Then part B was saying that find the period of the wave. We've just got the period of the wave, 0.1 seconds. Okay, we've just got that. Then Roman 2, the progressive wave, which will give a stationary wave with the one above. So part B here was saying that the period, you've just seen that in the case of to get the period, then we see in the case of to compare the two, we shall end up with 0.1. So our period t is equal to 0.1 second. Just from here, you can quote this. When try to compare that with what we have here, with our equation, to give us 0.1. And then part C is talking about a stationary wave. What is a stationary wave? What do you remember?
The waves formed when two waves of equal frequency and amplitude traveling at the same speed in opposite direction are supposed resulting in two formation of a node and antinode.
Okay, so in other words, they're trying to give us you're combining the properties of when is a stationary wave formed? You remember
when two waves of the same frequency collide, but they're moving in opposite directions.
Okay, number one, two waves must be moving in opposite directions and they meet, they interfere. Okay, so if the two waves are moving in opposite direction and then they meet, we expect to form a stationary wave. Those two waves must be having the same frequency, the same wavelength, like that. And if you had formed a stationary wave in this case here, it is very simple. What we need to do is to look at our equation, and where there's a minus, simply make it a positive.
Oh, okay.
Yes, just that. That's what I can say there. So if those two waves meet, then we expect to get a stationary wave. We shall be talking much more about interference when we reach things to do with. Let me see here. With interference in detail. Okay, so Roman, number one is done. Number two is saying that two waves of frequency, 256 Hz, quote that figure there somewhere, number two. Two waves of frequency 256 Hz and 280 Hz, respectively, travel with a speed of 340 meters per second through a medium. Find the phase difference at a point 2.0 meters from where they were initially in phase. Okay, so you've been given these values there. Number two, we've been given that the frequency for the first wave is 280.
Yeah. Wait, isn't it 256?
Hey, okay.
256.
256, no problem. Is equal to 256 Hz. Sorry, my pen is misbehaving here. I guess it is out of battery. Okay. So 256 Hz. Then the second one was?
Bug fixes.
Oh, no problem.
It's lagging.
And then your name is.
Yes. So the second wave was having a frequency of
80. 280.
680, the velocity is 340.
340.
Okay.
Phase difference is 2 meters.
Okay. 280 has, then the velocity is equal to 340 meters per second. And then our distance x is equal to 2.0 meters. So we're having two frequencies here, meaning that we're having two velocities. Oh, two waves of frequency, yes, two waves of frequencies, those. And they travel with the same speed, which is 340 through a medium. Find the phase difference at a point 2 meters. Now, what do we say phase difference is? Find the phase difference.
When the wavelength leaves the other by half a wave.
Mm-hmm.
When one leaves the other by half a wavelength.
Yes, is that's how we define the phase difference?
Yeah, an occurrence when one wavelength leaves the other by half a wavelength.
Okay, mathematically, the phase difference, we can simply call it the difference in the phase angles.
Okay.
Yes, phase angles. When you say that when one leaves the other by a half the wavelength, it means that it simply means this. That, for example, in case we have one wave here, this, and then we get another wave here, for example, starting from this point here, and it goes like this. So if this one is having, let me call this one, the distance from this point to this point is what we call the a half of the wavelength. I hope that is okay. From here to there, that is what we call the wavelength, okay?
Okay.
Yes. Now, if one wave starts from, if the red wave and then the blue wave are having a difference in the phase angle over half the wavelength, this is what we mean. The phase difference will be 2 pi. I mean, it will simply be pi, or a half of the wavelength, like that. Now, coming back to this one here, if you are to solve this, then we need to get two phase angles for the two waves. For the two waves, we shall have to get the two phase angles and then we subtract them. That is what we are going to do here. Now, how do we find the phase angles? From the other expression that we had, you remember that, let me take you back here. The phase angle is given by this expression. Can you see that?
Yeah.
Phase angle is given by this expression.
2 pi over lambda x.
Now, given this equation here for the phase angles, we can try to use the same for the two equations here. I mean, for the two waves here. So I need you to find the phase angles. My writing pad is becoming an issue. Okay, so using this. Okay, using these two frequencies here, this one and this one, and the wave velocity and the distance, and our equation phi being given by 2 pi divided by lambda times x. I need to find phi 1, then I need to find phi 2, and then get the phase difference. So our phi 1 will simply be equal to 2 pi out of lambda 1 times the x. Our phi 2 will be equal to 2 pi out of lambda 2 times the x. And remember that our wave velocity is given by lambda f. So in case of the wave velocity and then the frequency, you can get the lambda. Okay, so you can get our lambda 1. It will be equal to 340 divided by the frequency, which is 256. Get our lambda 2, which is 340. It is the same velocity divided by 280. And then afterwards, you substitute these two into our expression here.
Okay.
And then afterwards, you get the phase difference, which will be the same as either theta 2 minus theta 1. You can get the magnitude. Or phi 1 minus the phi 2, and then you get the magnitude. So I'm waiting for that answer. I need to see whether you get this answer here. The answer here is 0.89 radians. You can get the value in okay, let me wait for the answer here. We have 3 minutes remaining. Okay, I guess we have too much to do, and
Very difficult.
so last time you said that we should be doing more calculations of this.
Yeah, because it's all well and good understanding the writing part, and then the numbers throw you off.
The number comes and squeezes you.
Yeah.
So you've got 0.89 radians.
Yeah.
And by the way, for me, I'm showing you maybe working from first principles, from the basics, from what you need to know. But in case you know what you're doing, you can just simply use one single equation and you summarize everything. And that's that someone can say that the phase difference is given by the formula 2 pi x into 1 over lambda 1 minus 1 over lambda 2. And then someone
I was about to say that, but I wasn't sure if it's correct.
No, it is just we try to simplify the two like that. That can be like the general equation. But if you understand it from first principles, then the better. Any way that you understand it, any way that you get it, it is very much okay. So that is number 2, as simple as that, like Christine is saying. Then number 3. Number 3 is there. The displacement of a wave traveling in the x direction at a time t is given by the equation y is equal to sine 2 pi 0.25 x minus 100 meters, where x and y are in centimeters. So this time around, we've been given x and y in centimeters. What is funny, you guys?
Yeah, relax.
You're always no. Don't even think we're okay. Okay.
We're laughing at Liverpool.
Okay, yes. I was saying that this question number 3, I guess it is very simple for us. They want us to find the wavelength and then the velocity. Number 3. You write it down here. Question 3. We've been given the equation y is equal to y is equal to sine 2 pi. Okay.
Wait, what?
Yeah, it is there. Don't worry. You can quote the equation. You can be doing it there.
No, like it was a bit like choppy, so I didn't see it properly. That's what I was saying. Wait, what?
Oh, it is equal to sine 0.25. I guess this one was t. Then minus 100x. Let me first move up. Y is equal to sine 2 pi 0.25x minus 100 meters. Minus 100 meters. I wrote it somehow different.
2 pi.
Okay, let me repeat. It was 2 pi into 0.25x, then minus 100t. So the part A was saying that find the wavelength, and then part B was saying that find the velocity. So, Christian, here you are. The question is yours. How do you find each of those?
Teacher, because we're saying it's easy doesn't mean.
No, the day was to discuss for us.
I was not informed.
We told you at the start.
Okay, yes, anyone can start for us.
Well, I feel like it's reversed. Like if you relate it to like this first equation you're saying related to, like I feel like it's reversed.
Y is equal to A.
Like shouldn't the A be this side and the 100 acres and the 100 is on this side?
So it was T out of capital T. Then minus.
Yeah, and then minus x over lambda.
Okay. Oh, okay. So then after that, yes, after that, what do we do?
You said we could use velocity. The bad thing is that velocity wasn't given because you said we could use velocity to find one of these if the other wasn't given.
Let me take it back to number 1. Number 1 is here. That's what we did.
Wait, isn't it like I think it's 0.25 because if it's like x over lambda, you can take the x as 1 over. Could you?
Oops. You're saying something? Okay.
Valentine's is coming.
I guess I will send him the recording. So as you're seeing in this working of hours, I've ignored the negatives. on purpose.
Uh,
I've given what the negative
Okay.
on purpose, simply because the negatives in that equation there simply give us the direction of the wave. And maybe where it started from. So, in case you want, by the way, you can write this lambda in centimeters, and then you get your answer as 400 centimeters per second. It is also,
when she's
it is
over
also,
it,
it is also allowed.
or it's okay.
It is also allowed. If you set them, it's very well. If you set them, it's very well. But that is what we can say about this number here. Then let's try out some 2, 3 numbers in the exercise here. Number 1. I'm going to leave out number 1 for you. You'll try it out. I'm going to send you this document. Number 2.
It's similar.
Number 2 is also.
No, haven't we just done number 2?
Actually, they resemble.
Yeah, we've just done number 2.
They resemble with number 3. Yes. Resemble number 3. Then
yeah, it's just that the units are different. Like for it, the answer is in meters, while for us, our answer is in centimeters.
Oh yeah. So the working is the same.
Yeah.
Then number 3, the displacement of the wave traveling in this direction at time t is y is equal to that in meters. The velocity of the period, even that one is also very simple. Then number 4, we have not yet done it. This.
Yeah, I was looking at that. I was looking at this.
Number 4, we have not yet done it.
What?
I was like, what?
Okay. So I guess I'm going to stop here for now.
So it's just
just
number 1 and number 3, because like
number 1 and number 3.
Number 4, yeah, because like number 4 and number 5 we haven't yet.
Number 4
covered that.
Number 4 onwards, you leave them out. Yes, please.
You could find a separate exercise and then like you could send it and then yeah.
It is okay. Or you can simply take a screenshot.
Okay.
Take a screenshot. Number 1 and then number 3. And by the way, in case you have a question bank, you can look at the question bank. There are very many questions related to what we've just discussed. Let me first pause the recording here.